All right, so good morning, everybody. Today, we're going to mostly finish up what we're doing with square roots. And so what we're going to do is we're going to talk about, make sure I get this order correct here. We're going to review multiplication a little bit. Of square roots. Partly because I didn't necessarily get to finish that, or I didn't do as many examples at the end of the last lecture as I really wanted to. So we're going to do that. That's out of section 9.4 of your book. And then in 9.5, we're going to look at rationalizing denominators and what that means when we talk about rationalizing a denominator in a square root expression. We're going to look at ones where the denominator is one term, and we're also going to look at where the denominator is two terms. And so we're going to look at what that means and how you go about doing rationalizing denominators. And then in section 9.6, we're going to look at solving equations with square roots in them. We probably won't finish that today, but we'll get into that certainly. So the main sections here, we've already covered 9.4. We covered 9.4 last time. And so, but I want to do some reviewing out of 9.4, and then we'll look at section 9.5 and then 9.6. All right, so first of all, another thing to mention here is that remember exam 1, you should be looking at your grades in exam 1 that I've posted those on your WebAssign grade book. And so you should hopefully be able to find those, and that if you want your graded exam back, that you need to go ahead and email me, and then I will respond to your email and attach a copy of the graded exam. So, and I have not gotten to that yet. I just finally got all the graded exams uploaded where I needed to get them uploaded last night, but I will be doing that today. So and so if you email me today or tomorrow, and some of you have already emailed me, but if you email me today or tomorrow, then I will send you back your graded exam. So we're also starting to think about exam 2. The review for exam 2 is going to go up, I would say, probably by next Tuesday or Wednesday. And hopefully by next Tuesday, maybe by the time we meet again for lecture next Tuesday, it'll be up already. I'm not sure, but and the exam window opens 2 weeks from today, so so exam 2 is already coming up relatively quickly. So, all right, so multiplication. And just some highlights of multiplication that we really need for the rest of the chapter, that we need to go back and kind of go back over again. First thing is that something that I think is important is that we talked about this some last time, that if you take a square root and multiply it by itself, so the square root of 3 times the square root of 3. For example, two ways to look at that. You could look at that as the square root of 3 squared, or you could look at it as just the square root of 9 because you're multiplying two square roots together, right? And so that means you can multiply them. But either way you look at it, square root of 9 is 3. Square root of 3 squared is 3. Because remember, the square root process and the squaring process are kind of sort of, not exactly, but kind of sort of inverse processes. So it's like they undo each other. So if you take the square root of a number and square it both, it's like you're not doing anything at all. then you get 3. Now that property doesn't work if you've got a negative number, but if it's a positive number, then it works. So the idea here is that as long as if you have the square root, if you have the square root of Bob times the square root of Bob, as long as Bob is positive or 0, then the square root of Bob times the square root of Bob is always going to be just Bob at the end, right? That if you take a number, a square root of something times the square root of that same thing, you're always just going to undo the radical essentially and just end up with what's underneath the radical, because it ends up being a square when you do that. All right, so that's an important thing to know and be able to just write down when you see it. So, if you know that x is positive, then you know that the square root of x times the square root of x is going to be x. And the square root of 17 times the square root of 17 is going to be 17. Remember, the only time that property is not true is when you have negatives underneath the square root. Negatives underneath the square root is something we have not talked about yet. All we've talked about is that those represent non-real numbers, but right now we're going to leave that just kind of as an open question, and we'll deal with that towards the end of this chapter, or actually at the very end of this chapter. So, all right, so that's one thing you need to know with square roots. I wanted to go back over that again and make sure that you were good with that. The next thing, multiplying conjugates when you've got square roots. Now remember, conjugates, we've used that term before, is when you're multiplying things like this, a plus b times a minus b. Now, a plus b times a minus b is the exact same expression, notice, but one of the terms or one of the factors has got an addition and one of them's got a subtraction, right? So the signs are different right here. And remember, when you multiply conjugates, a plus b times a minus b is just the difference of two squares, and you end up with a squared minus b squared. So if we multiply conjugates together and you've got square roots in it, watch what happens. So if you have the square root of 2 plus 3 times the square root of 2 minus 3, all right, those are conjugates right there, because that would be a plus b and a minus b. So what does that pattern say off to the side? Well, that pattern says that this should be a square minus a square, and that's the way you should write it. You should write it as just a square minus a square, and when you do that, you end up, you have the square root of 2 squared there and 3 squared there. So notice that square root of 2 squared is just what we were just talking about a second ago, that when you take a number and take its square root and then square it, it's like you're not doing anything at all, right? So you end up with a 2 right there. And then 3 squared, now that's not a square root, so that's 9. And you end up with negative 7 as the answer. Now, the important thing that's going on here when you're multiplying conjugates is that notice that you started with square roots. So you started with square roots in the expression, like that, but you finished after you multiplied with no square roots. And that's always going to be true when you multiply conjugates together. If you have square root expressions as part of the conjugates, you'll always end up with things that don't have any square roots in them at the end. Right? That's when you're multiplying conjugates together. And so that's actually going to be an important thing for us to know. So let's say we have the square root of 10 plus the square root of 5 times the square root of 10 minus the square root of 5. Right, so again, those are conjugates, right? One's addition and one's subtraction. They're not the same expression, but they're close. It's just that one's addition and one's subtraction. So as soon as you see that you've got conjugates there, as soon as you see that you've got that, then just write down that, hey, I know that that's a square minus a square. And I'd literally write down the parentheses, and I'd put a square and minus a square there. And all you're doing is filling in the parentheses with the terms that you've got in your conjugate expressions up there. So this is the square root of 10 squared minus the square root of 5 squared. And then the square root of 10 squared, there you go. There's a square root that's squared. And so what do you know? You've got, that's going to be just 10, right? When you take the square root of something and then you square it, it's like you're not doing anything at all. And because it's like processes that undo each other. And so you end up with 10 there. Square root of 5 squared, once again, it's the square root of something squared. And so that's 5. And you end up with 5 as the answer. And so notice we took two square root expressions, multiplied them together, and the two square root expressions are conjugates. And when I multiply them together, I get something that doesn't have a square root in it. Only works for conjugates. That's the only time that that kind of thing is going to happen. So, you know, I want to kind of emphasize that also. So let's say we have 3 square root of x plus 4 square root of y. And so if I was going to multiply that by its conjugate, right, what would the conjugate be? It'd be 3 square root of x minus 4 square root of y, right? That's my a plus b times my a minus b. And so I've got conjugates there. I've got that form. And so what can I do? I know this is going to multiply out as a square minus a square. And so then just fill in the parentheses with the terms. So that I'd have 3 square root of x there and 4 square root of y on that one. Now be careful when you square this. See, look, because the 3 square root of x, that's there's two factors in there. There's a 3 and a square root of x. You're squaring both of them. So that's 3 squared and then the square root of x squared. The 3 is not a square root, right? So you're squaring that and you're getting 9. But the square root of x squared, again, x is positive. We're always assuming these variables are positive here. Then the square root of x squared is going to be x, as long as x is a positive number. And the same thing on this second term. I'm squaring the 4, and I'm squaring the square root of y. And so 4 squared is 16, and the square root of y squared would just be y, right? And y is positive also. Now we got some variables in there, but notice no square roots, right? We started with an expression that had square roots, and we finished with an expression that does not have square roots. And so every time you multiply conjugates together like that, that's always going to be true. Let me probably do one more example like that, and then we can go on to another kind of multiplication that I want to go back over again. So let's say we have 7 square root of 2 minus 4 square root of z. And so if I was going to multiply that by its conjugate, the conjugate would be 7 square root of 2 plus 4 square root of z, right? One of them subtraction, one of them's addition. They're not the exact same factor, they're just close. So since I've got conjugates there, I know that this is going to multiply as a square minus a square. And so I fill the blanks in. In this case was 7 square root of 2 right there, and 4 square root of z right there. All right, so now you square 7 square root of 2. And just like the problem we did a second ago, that's 7 squared and the square root of 2 squared, right? The 7 is not a perfect is not a square root, and so when you square it, you just get 49. But the square root of 2, that is a square root. So when you square the square root of 2, you just get 2. Right? You get the number that's underneath the square root. It's the exact same thing's going on with the 4 and the square root of z. So this is 4 squared and then the square root of z squared. And again, I'm assuming that z is positive here. And so that gives me 16. 4 squared is 16. and then the square root of z squared. It's like, they're undoing each other there, and so that just ends up giving you z. Get the number that's underneath the radical. You can do a little bit of multiplication there. You get 98 minus 16z. And what happened? You started with an expression with no square roots, or with square roots rather, and you ended up with an expression that did not have any square roots in it. All right, so so that's multiplying conjugates together. Going back to this page right here, this is what we were just talking about, multiplying conjugates, right? Expressions that look like this, a plus b times a minus b, where you've got some square roots in the expression. All right, so now the next type of multiplication I want to do, so we're still talking about multiplication. We did talk about this a little bit last time, but didn't work enough examples that I felt like we had enough to see there. What I'm looking at here are perfect squares. So a perfect square, I'm talking about something like this. I'm talking about either a plus b squared or a minus b squared. But the a and the b are going to have some square roots in them, is what we're looking at specifically in this chapter. Now, when you square a plus b or square a minus b, and we've talked about this before, you end up with this expression. You could go through and use the FOIL method to do this, but you end up with a squared plus 2ab plus b squared for a plus b squared, and for a minus b squared, you get a squared minus 2ab plus b squared. You almost end up with the exact same thing there. First, one other thing to mention here is, remember, these are not conjugates right here. Remember, a conjugate expression, which we were just talking about in the last couple of screens, is like when you have a plus b times a minus b. But perfect squares, these expressions aren't close to being the same. They are exactly the same. So a plus b squared is a plus b times a plus b, right? Both are addition. And a minus b squared is a minus b times a minus b. They're both subtraction there. So make sure you understand that conjugates are expressions where one's addition and one's subtraction, but perfect squares, they're either both addition or they're both subtraction. All right, well, we want to take advantage of this pattern right here, that when you square an expression in the form a plus b or a minus b, that you end up with either a squared plus 2ab plus b squared or a squared minus 2ab plus b squared. And so that's what we want to look at here, and what that means when you've got square roots. So let's say I have the square root of 3 plus 5, and that is squared. Okay, so as soon as you see that you've got a square like that, it's not a conjugate expression, it's not one addition, one subtraction, these are both addition. Then you're talking about this pattern, a squared plus 2ab plus b squared. And so what I would do here is I would set this up with parentheses. I put parentheses squared plus 2 times parentheses plus parentheses squared, like that. Right, that's kind of our pattern here. And then fill that in. I'm going to put this as a separate step so you can kind of get an idea of what I'm doing. And then fill it in with the numbers that you've got. So the square root of 3 goes in there, right? That's the a. The square root of 3 goes in there, and then the 5 goes in there, and the 5 goes in there. Right, and that's a squared plus 2ab plus b squared. And then do the multiplication. So the square root of 3 squared is 3. Right? You take the square root of a number and then square it, you end up with the number underneath the square root. The next one is a multiplication problem. You have 2 times the square root of 3 times 5. The 2 and 5 are not underneath the square root, so you multiply those together and get 10, and the square root of 3 just comes along. So you have 10 square root of 3. And then the 5 squared is 25. It's not a square root, so it's just squaring 5. And then you do have some like terms here at the end. The 3 and the 25 add to give 28 times 10 or plus 10 times the square root of 3. Remember, you cannot add the 28 and the 10 because you would be violating order of operations, and so that would be our expression. Now, notice you do end up with a square root in there. That's not the point. This is gonna be a play into how we deal with equations, believe it or not, in a couple of sections. So that's why we're talking about this kind of multiplication. It's going to come up again for us. All right, so let's look at another example. Let's say we have the square root of x minus the, let's say, the square root of y, and that is squared. Right, so it's the square root of x minus the square root of y, quantity squared. So when you have a perfect square like that, once again, right, like we've got over there on the side, in this case, this is going to be a squared minus 2ab plus b squared. That's our pattern in this case when we square a subtraction problem. So you're going to have a square minus 2 times 2 expressions like that, and then plus a square. Right, that's our pattern. And then fill in the blanks with the terms that we've got in this particular multiplication problem. So the square root of x goes in there, and the square root of x goes in there. And the square root of y goes in there, and the square root of y goes in there. And then do all the arithmetic. So the square root of x squared, as long as x is positive, is going to be x. Right? You're squaring a square root, you end up with the number underneath the square root. In the middle term, there's nothing to do there except I can take the square root of x times the square root of y and actually multiply them together and get square root of xy. And then the square root of y squared, as long as y is positive, is going to just be y. And at the end there's not really any like terms or anything like that, so that would actually be my final expression in that case. X minus 2 times the square root of xy plus y. All right, so definitely wanted to go back over perfect squares again and make sure that you were kind of okay with that as well. We're going to be using these things in the rest of class today, so that's why I needed to go back over some of this multiplication again and make sure that you saw some examples. All right, so now what we're going to do, are there any questions before I go on?
If there was a negative x square root, it would be like a negative x to square root of xy plus y.
If there's a, Janessa, where are you talking about the negative sign being?
Where the square root of x square is, like if it was a negative.
You're never going to have negatives in there in these problems. Okay. You're always just using those terms. So this is always your a right here, and this is your b. And you don't care about that minus sign in the middle. That minus sign carries over. That minus sign right there is the same as that minus sign and that one right there. And so you don't have to worry about signs anywhere through this if you're using this pattern here.
Okay.
Is that okay?
Yeah.
All right. That didn't sound real positive, Janessa, but you sort of. Now you're going to, and the thing there is you're going to need some practice, and so you can watch me do these kinds of problems on the screen, and you think you understand it. And Janessa, this isn't just for you. This is for everybody. This is probably all of you have had this experience, though. You go through and you're watching me do these problems on the screen. And, it looks, you start saying to yourself, well, I think I understand this. I think I understand what he's doing and everything. But then you go to your book after lecture is over and you try to do these problems on your own, and then you have some trouble with it a little bit. And so, make sure that for all of you guys, for you guys who are attending live right now, and for all of you who are going to watch this later, make sure you do some practice. You got to do some practicing, not just out of web assignment, but out of the textbook, and get some problems done here and actually work through some of them on your own. You get these notes out in front of you and work through some problems, referring to the notes constantly. That's fine. But then gradually start referring to your notes less and less and getting through the problems kind of on your own more and more. So that when it's time to take the test, you're working these problems by yourself with no problem. And I know it doesn't sound like a lot of fun maybe necessarily, but that's the way you're going to be successful on this next test, because this next test is just going to have square root stuff all over it. And so you've got to go through and get some practice on this so this kind of stuff becomes more and more natural to you. Does anybody else have any questions that they want to ask before we get moving on this stuff?
No questions.
All right. Jose, it sounds like he's good. All right. Then no questions so far. Then our next step here is to talk about rationalizing denominators. Whoops. This is section 9.5, and we want to talk about rationalizing denominators. All right. So first of all, and this is something like in my college algebra class, by the way, that we are confronting frequently right now in class. But numbers like 3 and 1/4 and negative 2/3 and 0.83 and things like that, and 0 and negative 8, we could throw those numbers on the list. Those are all what we call rational numbers. Those are rational numbers. Rational numbers are numbers that can be written as fractions, basically. And so all those numbers, negative 8 can be written as a fraction, negative 8 over 1. 0 can be written as a fraction, 0 over 1. 0.83, that decimal, can be written as a fraction, 83 over 100. Those are all examples of rational numbers. And then numbers like this, square root of plus or minus the square root of 2, or 1 plus or minus the square root of 5. Pi is an example. These are all examples of what we call irrational numbers. All right, so now we don't really care about numbers like pi at this point, but numbers like square root of 2 or square root of 5 or 1 plus or minus the square root of 5, those are all examples of irrational numbers. Those numbers have decimals that never terminate, never repeat, and they cannot be written as fractions, as it turns out. There's no way to write them as fractions at all. For various reasons, sometimes when you have a irrational number in the denominator of an expression, so like 3 over the square root of 5, it may be to your advantage. Notice I'm not saying it has to be to your advantage, but it may be to your advantage to write it so that the number in the denominator is not an irrational number, but that it's a rational number. So a lot of times when you have something over an irrational number, you want to come up with a way to rewrite it. So that's a fraction right there. This is a fraction bar right here. You want to somehow come up with a way to rewrite it so that the number underneath the fraction bar is a rational number instead, so that it doesn't have any square roots in it. So this one we'll say has square roots, and this one no square roots right here. I do not call this simplifying an expression, because you're going to find that some of the expressions we got, the answer is more complicated than what we started with. But the point is we're trying to rewrite the fraction so that there's no square roots. And my calculus students sometimes run into problems where it's going to be easier to do the problem if they can rewrite it so that there's no square root in the denominator like that. And so it's a process that's used sometimes in simplifying different kinds of expressions and making them easier to work with. And so that's what I want to teach you here, is how to do that. And so what we're going to do is we're going to kind of break this up into two two types of rationalizing. So let's say rationalizing where the denominator is one term is the first thing we wanted to look at. So like 3 over the square root of 5 is an example where you have a square root in the bottom, right? But it's just one term in the denominator. And so what we're trying to do, remember with a fraction, what you're allowed to do, what's legal to do, is to multiply the top and the bottom by the same thing. And so in this case, we're trying to get rid of that square root of 5 in the denominator. And so what we've just talked about with multiplication, we can accomplish that by just multiplying the denominator by the square root of 5. In other words, multiplying it by itself. And whatever we do to the denominator, we have to do the same thing to the numerator because we're only allowed to multiply by the number 1, which means the top and the bottom have got to be the same expression. So look what happens here. What do you get in the denominator? You get the square root of 5 times the square root of 5, right? And remember what we've talked about now is the square root of Bob times the square root of Bob is just Bob. Right, and so it's just Bob, right? As long as Bob is positive. So when you multiply a square root by itself, you end up with a perfect square, and it means the radical goes away. So the square root of 5 times the square root of 5 is just 5. Now in the numerator, you've got a 3 and a square root of 5 that you're multiplying, but one of them is a square root and the other one's not a square root, so you're just kind of stuck with that as a multiplication problem. And you leave it like that. And so what we're saying here is that if you have 3 over the square root of 5, we're saying that that's equal to 3 times the square root of 5 over 5. You can see why I'm not saying it's simplified because the new expression is actually probably slightly more complicated than the original one. But the deal here is that this first one is not rationalized, right? It has a radical in the denominator. This one is rationalized. No radicals in the denominator. Right? And so that's what we're trying to do here. This is the process of rationalizing the denominator. And the easy thing here is that if you have just one term, right, that's what we're talking about, rationalizing with one term right here, one term in the denominator. And let me actually kind of highlight that so it really separates itself. Like that. Okay, and so we've got it rationalized. All right, so let's look at another example. Let's say we have 8 over the square root of x. As long as x is positive. Then to rationalize this, right, we have a square root in the denominator. To rationalize this, we multiply the denominator by itself. Get the square root of x. But what do we have to do to the numerator? To do the same thing, right? So you multiply top and bottom by the square root of x. And so what do we get in the denominator? You have the square root of x times the square root of x, which is the square root of x squared, or just x. Numerator, one of those is a square root and one of them is not, and so we just write it as 8 square root of x. All right, let's say we have, so we're going to look at several different situations where you have just one term in the denominator. Let's say we have 2 over 3 times the square root of 7. Now in the denominator, in this case, what's the square root? Or what's underneath the square root? What's the radical? It's the square root of 7. That's what we're trying to get rid of from the denominator. We don't much care about the 3. So I'm just going to multiply by the square root of 7. And in the numerator, then, I got to multiply the same thing by the square root of 7. Remember, you're always multiplying top and bottom by the same thing. And so what do you get here? First of all, the numerator is just 2 times the square root of 7. But in the denominator, this is 3, and then square root of 7 times the square root of 7 is 7. So you have 3 times 7. And then multiply that out, certainly. And so you have 2 times the square root of 7 over 21. And that's the rationalized version of the first number that I wrote down. Right? So again, this is not rationalized at the beginning because it has a square root in the denominator. So this one's not rationalized. This one is rationalized right here because there's no square root in the denominator. All right, if you have the entire fraction underneath the radical, so let's say we have something like, well, let's say 7 over the square root of 40, or square root of 7 over 40. Now, what I would do in a problem like this, if you have a fraction underneath the radicals, I would first rewrite it so you have the square root of the numerator over the square root of the denominator, like that. So I'd write it as the square root of 7 over the square root of 40. Now, there's a couple ways to deal with this problem. First of all, I wanted you to notice that the square root of 40 does simplify because 40 has a factor that's a perfect square. And so I would simplify the square root of 40 first. So simplify first, then rationalize. So don't worry about rationalizing right now. Instead, just worry about simplifying the square root of 40. Now remember, and we had a long discussion about this probably over the last 2 lectures, but the square root of 40, if you want to break that up, you know, you're looking for factors of 40, and so like 5 and 8 are not factors you want to use because neither of those is a perfect square. But what you do want to do is use 4 and 10 because 4 is a perfect square, right? Don't forget that you want perfect squares as factors, or as one of the factors there. So I break up the square root of 40 as the square root of 4 and the square root of 10. And so then that's the square root of 7 over 2 times the square root of 10. All right, and now you can rationalize the denominator. Now it looks like the problem we just did, kind of, sort of. So you multiply the bottom by the square root of 10, and so that means I have to multiply the top by the square root of 10 also, because the square root of 10 is the only thing I'm trying to get rid of there. So in the bottom, you have 2 times the square root of 10 times the square root of 10. So the square root of 10 times the square root of 10 is 10. Right? And so that gives you 2 times 10. In the numerator, the square root of 7 times the square root of 10, both of those are square roots, and so you can multiply them and you get square root of 70. And then you've got the square root of 70 over 20. Remember, you can't reduce that because the 70 is under a radical and 20 is not, and so that's your rationalized fraction right there. Right? So believe it or not, these 2 things I'm putting the boxes around, those are the same number, but the second one is the rationalized version of the first one. Right? All right, so now flipping back the screen here, what are we doing? We're rationalizing where the fraction has 1 term in the denominator. All right, and so now what we're going to do, let's see, go to a new page here. Now we're going to rationalize, but the fraction has 2 terms in the denominator. And so that's what we're going to try to do, is figure out how to do that kind of rationalizing. These are harder to do. You're still trying to rewrite the fraction so that it doesn't have a square root in the denominator. So let's say I have 3 over, let's say, the square root of y plus 4. Right, so notice that in this problem there are 2 terms in the denominator. And so what we're trying to do is rationalize in this case. This no longer will work. This will not work to just multiply by the square root of y over the square root of y. Because when you do that, right, all I have is the square root of y in the denominator. But when you do that, in the numerator you have 3 square root of y. In the denominator, you would be using the distributive property here. And so the square root of y times the square root of y would be y. You'd get rid of that radical. But notice now you'd have 4 times the square root of y. And so you still have a square root in the bottom. And so the problem here is that this first fraction is not rationalized. And the second one is not rationalized either because it still has a square root in the denominator. And so this did not work. This does not work when you have 2 terms. And so what do we do instead? Well, we go back to something we talked about earlier in class today, earlier in the lecture. If you go back, and let's see, I'm going to look at multiplying. Here we started talking about multiplying conjugates together. And notice, what did we talk about? That when we multiplied conjugates together, we started with an expression with square roots and we finished with something that did not have square roots. And that's what we're going to take advantage of here. That's what works to get rid of the radical. So to rationalize when you have 2 terms, multiply top and bottom by the conjugate. That's the key here. The conjugate of the denominator. Okay, so in our problem, what is the conjugate of this denominator? Well, it would be the square root of y minus 4. And you do the same thing to the numerator. Square root of y minus 4, like that. All right, so when you do this, the numerator, just leave it as a multiplication problem. Don't multiply it out, just in case something reduces at the end. So just leave it as 3 times the square root of y minus 4. But in the denominator, what are we doing? We're multiplying conjugates, a plus b times a minus b. And so this ends up being a square minus a square. Remember, that was the pattern for conjugates. And so this would be the square root of y right there and 4 right there. And so you'd end up with 3 times the square root of y minus 4 over the square root of y squared, as long as y is positive, is y, and 4 squared is 16. And that is the rationalized version of the original fraction. So notice this is very clear why I'm not calling it simplifying. There's my original expression. This is my rationalized expression. And notice the rationalized expression is more complicated than the first one, certainly. So I'm never going to say that that's simplifying the expression, but I will ask you to rationalize things like that in most cases. So, all right, so that looks good. I'm in your book on page 1072. This is section 9.5's homework, and this is problem number 368. So 368, you have the square root of 5 over the square root of n minus the square root of 7. Like that. And so clearly that expression is not rationalized, right? I have square roots in the bottom. And so my goal is to get rid of those square roots. And so what do I do here? I multiply by the conjugate of the denominator right here. And let me shade that little statement right there so it kind of stands out on the page, right? That this is what you're talking about. If you've got 2 terms, you multiply by the conjugate of the denominator, right? And so in this case, I'm multiplying the bottom by the square root of n plus the square root of 7. And then I have to multiply the numerator by the same thing, the square root of n plus the square root of 7. All right, so in the denominator, that's the part that we're really interested in. That's a square minus a square. And so I put the square root of n in there and the square root of 7 right there. And in the denominator, as long as n is positive, as long as n represents a positive number, then the square root of n squared would be n. The radical goes away. And then the square root of 7 squared would be 7. The radical goes away there. You just end up with n minus 7. In the numerator, you've got the square root of 5 times the square root of n plus the square root of 7. And in a problem like that with square roots, as one of the factors, you'll see it both ways. You'll see it just written out like that, and sometimes you will see it multiplied out with the distributive property there. So you get the square root of 5n, right? Because square root of 5 times the square root of n, they're both square roots, so you'd end up with the square root of 5n. And then this would be the square root of 5 times the square root of 7 would be the square root of 35. I'd actually take that numerator either way. Frankly, don't know what WebAssign will do there on a problem like that. So, let's see, what did I do wrong there? It should be square root of n right there. So try it both ways as far as multiplied out and not multiplied out. So and see what happens. All right, let's do one more problem like this, and then we're ready to tackle equations for the last part of class. So this is problem number 372. And on the same page, and you have the square root of s minus the square root of 6 in the numerator. And in the denominator, you have the square root of s plus the square root of 6. Right, so this is an example where you've got a fraction where there's two terms in the denominator, and you're trying to rationalize. So this is a classic example where to rationalize this, you would multiply the bottom by its conjugate. So that would be the square root of s minus the square root of 6. And then you multiply the top by the same thing, the square root of s minus the square root of 6, like that. All right, so in the denominator, what am I doing? I'm multiplying conjugates together. And so that would be, hold on, let me change the color back here. So that would be a square minus a squared, like that. Now, interestingly, in the numerator, those are not conjugates. Those are actually the same expression. And so that's actually the square root of s minus the square root of 6 quantity squared. That's actually the other multiplication pattern that we were talking about. So if you remember that pattern for that problem, this is probably good to look at so we can compare the two patterns. This one is a square minus 2 times the product and then plus a square, like that. Remember, that's a squared minus 2ab plus b squared for the numerator. The denominator is just a squared minus b squared. That's the difference between conjugates and squares right there. So in the denominator, I have the square root of s goes in here, and the square root of 6 goes in here. And that denominator then would just be s minus 6, as long as s is positive. And in the numerator, I put in the square root of s, and the square root of s, and the square root of 6, and the square root of 6. And so you end up with, in the numerator, you end up with s minus 2 times the square root of 6s plus, not plus 36, hardly. A square root of 6 squared would just be 6, like that. Do not try to cancel those s's or those 6's at the end because you've got terms. These are terms at the end there, so no canceling. In fact, there's no factoring to do of any type whatsoever, so that would be your final expression right there, and that would be the rationalized version of the original fraction. Okay, so we've talked about rationalizing with one term in the denominator, and now we've talked about rationalizing with two terms in the denominator. And so, and lots of practice with multiplication. And you can see definitely that one thing you're going to have to do is just practice this and and work through problems so that it becomes a little bit more natural to you to do things like this, and that so that you can do these kinds of problems without any notes in front of you, right? Write lots of steps out and concentrate on these patterns that we've talked about. The difference of squares for conjugates right there, and then this is a perfect square pattern right here. So kind of really watch for that. All right. So if there's nothing to ask, does anybody have anything to ask before we move on here?
I have a small question.
Justin, go ahead.
Why did the sign change on the denominator at the start of the problem?
To remember what you're going to do if you have two terms in the denominator, that what you want to do is you want to multiply. You're trying to get rid of all the square roots, and the way to get rid of all the square roots is you're trying to get this pattern right here where you have a square minus a square. Because if you can get a square minus a square, then all the square roots are going to go away automatically. But what kind of multiplication gives you a square minus a square? It's when you've got conjugates, right, where one's addition and one's subtraction. So we started out with an addition problem and the denominator, and so what did we have to do? We had to multiply by the conjugate of the denominator, right? So we're multiply by the conjugate of the denominator. So you're trying to figure out what you got to multiply by to rationalize it, right? And so if the denominator is a plus b, in other words, if it's addition, and who cares what the numerator is, but if the denominator is a plus b, then what are you going to do here? You're going to multiply by a minus b and a minus b like that, right? You're going to always multiply by the opposite sign. And if the fraction is a minus b like that, if it's a subtraction problem, then what are you going to do? You're going to multiply by an addition problem, a plus b and a plus b. Because you're always trying to get rid of those square roots in the bottom, and the way to do that is to get conjugates in the denominator like that. A plus b and a minus b. Justin, did I address your question or not?
Yes, thank you.
That makes sense?
Yes.
Okay. Anybody else have a question?
Oh, not right now.
Everybody else is okay? All right.
I'm good.
All right, then let's. We are going to now look at solving equations. This is section 9.6. So solving equations with square roots. Figure out a way. Our goal is to figure out a way to rewrite the equation with no square roots. Right? That's what we're trying to do. Is figure out a way to do that. And the idea goes like this. So this, I'm on, by the way, on page 1088 of your book. And we're going to start off with problem number 394. And we're going to start off with some pretty simple problems to start off with, very simple problems actually to start off with. And we'll finish, not today, but next Tuesday, we'll finish with some problems that are pretty messy, pretty hard to do. Lots of steps. So page 1088, number 394, we have this equation, the square root of 7z plus 15 equals 6, right? And so it's an equation, a relatively simple equation that has a square root in it. And our goal is to figure out a way to rewrite the equations so that there's no square roots in the equation. And you've done that. You've solved equations, all sorts of different kinds of equations in algebra. So you've kind of had it beat into your head over the years that as long as you do the same thing to both sides of an equation, then you're okay, right? That the new equation is the same as the original equation. That's always okay to do. So you've done that constantly in your algebra careers, right? And so if you just off to the side here, if you have an equation like this, and I'm going to do a super simple equation, you have x plus 3 equals 15. Well, I mean, what do you know? What do you know to do? You subtract 3 from both sides of the equation, right? And you end up with a new equation, x equals 12. But what's always been true, that new equation, its solution is 12. And this original equation, well, its solution was 12 also. Right? That when you subtracted the same number on both sides of the equation, that you changed the equation. The equation's a new equation. It's a different equation. But its solution is the same as the original problem, that you don't change the answer to the equation. So subtraction works like that. Addition works like that. Multiplication works like that. Division works like that as long as you don't divide by 0. That as long as you do those things, the same thing to both sides of the equation, you don't change the solution to the equation. The solution is still the same. But the process that we're going to use for square root equations is a little bit different. What we're going to do here, when we says figure out a way to write the equation with no square roots, what we're going to do is we're going to square both sides of the equation. We're not going to add the same number to both sides. We're not going to subtract the same number from both sides. We're going to square both sides of the equation. And you might think that that's okay to do, that never is a problem, and in generally it's probably okay to do, but I want you to think about a simple equation like x equals 4. Simple equation. Its solution is 4. Now square both sides of that equation. If you square both sides, you end up with x squared equals 16. And the deal is, 4 is still a solution to that equation, but negative 4 is also a solution to that equation. And so what happened here is you picked up an extra solution to this equation. A solution that was a solution to the new equation, but was not a solution to the original one, like that. And so you actually picked up an extra solution to the equation when you do that. And so squaring both sides of an equation can do that. It can produce extra solutions. So squaring both sides, I'm going to write this at the bottom, notice I say can, it doesn't have to, but it can produce extra solutions. Those extra solutions, by the way, that are not really solutions to the original equation are called extraneous solutions in algebra. That's the word we use. Those are called extraneous solutions. And so you have to guard against getting extraneous solutions when you're solving an equation, when you're squaring both sides. And so the moral here, the moral to the story is you must check all solutions when you find yourself squaring both sides of an equation. And this comes up with college algebra students, and it comes up in calculus. And this is the fact here, is that when you are solving an equation, if you find yourself squaring both sides of the equation, then later on you know that whatever you get as an answer, you're going to have to check it and make sure it's actually a solution to the equation. All right, so all this stuff in red on this screen, that's what it was all geared towards, was this idea that squaring both sides, you must check your solutions to do that. All right, so now we've got the square root of 7z plus 15. With that out of the way, what are we going to do to get rid of the radical? We're going to square both sides of the equation. We're going to square both sides, and we're then going to make sure we check our solutions at the end. All right, so the square root of 7z plus 15, quantity squared, right? We have a square root that's squared. We've talked about that a bunch of times today now. We know that just leaves us with what's underneath the radical. And then on the other side of the equation, 6 squared is 36. And boom, what do we got? We've got an equation with no square roots. So no square roots, right? And we've accomplished our goal. We've got an equation with no square roots. And so we celebrate a little bit, and then we don't get cocky. We finish the problem. So we celebrate. You go, yay! I've got an equation with no square roots, and now solve the equation. Don't bail out and stop right there. That's a linear equation, and so just solve for z. So subtract 15 from both sides, and then divide by 7, and you get z equals 3. Now, we don't celebrate yet. We don't know if we've got a solution to this equation. What do we have to do? Remember what I was talking about down here. We squared both sides of the equation, so what do we have to do? We have to check our solution. So to check it, this is actually an easy check. Sometimes the check is going to be as hard as the problem. You've got the square root of 7 times 3 plus 15 equals 6. So you have the square root of 21 plus 15 equals 6, or the square root of 36 equals 6, and sure enough, you get 6 equals 6. Yay. And so our solution is 3. 3 is the solution to this equation. All right, so the idea here is square both sides of the equation, see if you can get rid of a radical by squaring both sides. And then when you square both sides, what else do you have to remember to do at the end of the problem? You have to remember to check your solutions because it could be an extraneous solution. And that is going to happen, by the way. All right, so this is problem number 398 on the same page. So on 398, you've got the square root of 2n minus 1 minus 3 equals 0. And so we've got an equation with a square root. We know we're going to square both sides, but one thing we need to do first here is before squaring both sides, make sure the square root is by itself. It doesn't do you a lot of good if it's not by itself, right? If it's not isolated on one side of the equation. So in this problem, before I square both sides, the first thing I'm going to do is I'm going to add 3 to both sides of the equation, right? You've got to move the 3 over. And that way the square root of 2n minus 1 is sitting there by itself. And now we are ready to square both sides of the equation. And I know that because I'm doing this, I have to remember to check my answers at the end of the problem. All right, so squaring the square root of 2n minus 1 gives me just 2n minus 1, right? You're squaring a square root, so you end up with what's underneath there. And then 3 squared is 9. And boom, once again, yay, we've got an equation with no square roots, right? So no square roots right here, no radicals left. And then solve the equation. And this is a linear equation, so you just add 1. You get 2n equals 10, 2n equals 10, divide by 2, and you get n equals 5. And then what do? You check n equals 5 to make sure that that's not extraneous. You always go to the original equation to do that. And so you stick 5 in for n and see what you get. And what do you get there? 2 times 5 is 10, minus 1 is 9. So you have the square root of 9 minus 3 equals 0. And you get 3 minus 3 equals 0. Yeah, you've checked it. And so 5 is our solution there. All right, so that should look okay. We have I definitely have a couple more problems I want to look at here. A couple of things to talk about, and we're going to gradually push the envelope here as far as the difficulty of the problems. Not just yet, but we will be in a second. So this is number 406. You have the square root of 3z minus 5 plus 2 equals 0. Square root of 3z minus 5 plus 2 is equal to 0. All right, so like we saw at the problem at the top, the first thing I want to do is get the square root by itself. And so I subtract 2 right there. And then go ahead and square both sides of the equation to get rid of the radical. So I square both sides like that. And so on the left side, I get 3z minus 5. And on the right side, I get 4. And once again, no square roots are left at that point. And so then I solve for z. I get 3z equals 9. Z equals 3. This was just a simple linear equation to solve at the end. And then I go through and I check. Z equals 3, and so I've got the square root of 3 times 3 minus 5 plus 2 equals 0. And so you get the square root of 9 minus 5 plus 2 equals 0. That's the square root of 4 plus 2. And notice you get 2 plus 2 equals 0, and that's not true. Right? You get 4 is definitely not equal to 0. Does not check. And so what happened here, you've got an extraneous solution, right? It didn't check. And so there's no solution to this equation because you've got to throw that one out. And so the solution set's no solution here. Now in this particular problem, you could have, if you had been observant, you could have told that that was what was going to happen. And you could have stopped it really at the second step right there. Because at that second step, a square root with a radical symbol like that is defined to be the positive square root of a number. And so the square root of 3z minus 5, it is not possible that it be equal to a negative number like that. And so as soon as you saw that you've got a square root equals a negative number, you're going to get, anytime you have the square root equals a negative number right here, you're going to get no solution to the equation. Right? There's no way that there could be a solution. Now, if you didn't notice that, then you could solve the problem and you'd catch it by checking it. But that would be a way of not having to go through the whole process there. All right, so that's number 406. The next problem I want to look at is problem, and let's see, let's look at problem 410, number 410. Problem B. There's actually two parts to 410, part A and part B. So let's look at B. So this is the equation, is the square root of z plus 100 minus z plus 10 equals 0. All right, so this is a little bit more complicated of a problem. Now, first of all, remember, we said get the square root by itself. So isolate the radical. So that's the first thing I've got to do is get the square root by itself. And so I leave the square root of z plus 100 alone, but I have to add z to both sides of the equation. And I have to subtract 10 from both sides. And so I get that the square root of z plus 100 is equal to z minus 10, like that. And now I've got the square root by itself. And now we go ahead and square both sides. Let's see, so I'm going to write this down again. But in this step, I'm squaring both sides. So square there and square there. So on the left side, the square root of z plus 100 squared is just z plus 100. You get what's underneath the radical. But the other side, you have z minus 10. That's a subtraction problem that you're squaring. And that goes back to the multiplication we talked about earlier in class today, this a minus b squared. And remember, the a minus b squared is a squared minus 2ab plus b squared, right? That's that pattern that we talked about for multiplying that out. And so that is what we get on the other side of the equation here. right? This is a square minus 2 times those two terms plus another square here at the end. And you've got a z there, and a z there, and a 10 there, and a 10 there. Remember, the signs have been taken care of, but that minus sign is simply that minus sign right there. So we've already taken care of the sign there. So you get z plus 100 is equal to z squared minus 20z plus 100. And notice in this step, the difference between this problem and what we've been doing is that this is now a quadratic equation, right? And so what do we know that we've got to have the equation set equal to 0. So this one's a little bit more involved because you end up with a quadratic like that. All right, so then we go ahead and solve that equation. So I'm going to subtract z from both sides and subtract 100 from both sides. So you get 0 equals z squared minus 21z, and then the 100s cancel out altogether. And then I factor the right side of the equation. So I factor, and then remember the first step for factoring something is to take out a GCF. So take out the z, and I'm left with z minus 21. And then I set each factor equal to 0, and I get z equals 0, and z minus 21 equals 0, or z equals 21. So I have two solutions here. And so I've got to check two things. I've got to check z equals 0. So every place I see a z in the original equation, I substitute 0. And I get that equation. 0 plus 100 is 100, so you have the square root of 100 minus 0. So that's just, so the minus 0 you can ignore, and so you're just left with plus 10 equals 0, and you get 10 plus 10 equals 0, and that definitely is not true. And so z equals 0 does not check. And so now we check z equals 21. So you have the square root of 21 plus 100 minus 21 plus 10 equals 0. And so that gives me the square root of 121 minus 21 plus 10 equals 0, or 11 minus 21 plus 10 equals 0. And that does check, right? Because you do get 0 equals 0 there when you do that. And so only 21 checks in this case. 0 does not check, and that's our solution. Then you have to tell me somehow that you're throwing one of those solutions out and keeping the other one. And so the way I did that right there would be just fine to do that. All right, so the moral to the story there is be really careful about checking your solutions at the end, and really this one step right here that I'm shading seems to be the most common mistake I'll see students make on a problem like this, is they will forget how to square something, and then they'll tell me that z minus 10 squared is z squared plus 100, and which it's not. So that's something you really got to watch for in this kind of problem. All right, so really watch for that. All right, so let's see. I would really like to work one more problem like that one so that you have another example before we shut down for the day. And so let me go ahead and let's say we have the square root, and this is just an example. This one's not in your book. Let's say we have the square root of x plus 8 minus 3x is equal to negative 2. Okay, square root of x plus 8 minus 3x equals negative 2. Now, just because it's equal to negative 2, don't say that's no solution. You don't know that at this point because that square root's not by itself. So what are we going to do first? We're going to isolate the radical. In other words, get the radical by itself. So the first thing I'm going to do here is add 3x to both sides. And so you get the square root of x plus 8 is equal to 3x minus 2. And now you're going to square both sides of the equation. Now the square root's by itself. And so I'm going to square, and I'm going to square. Right, so square both sides of the equation. So square there, and square there. And so the square root of x plus 8 squared is x plus 8. And then 3x, okay, 3x minus 2 squared. What have you got there? That's the perfect square expression again. And so when you square that, you've got to use this pattern, right? You have a minus b squared. You've got to use a squared minus 2ab plus b squared to square that out. Don't you dare tell me that 3x minus 2 squared is equal to 9x squared plus 4, because it's not. Right? You've got to use this pattern here, and you get this middle term that you're not going to get if you try it the other way. So you put a 3x in here, a 3x in here, and a 2 in here, and a 2 in here. And so I get x plus 8 equals 9x squared minus 12x plus 4. And I get a quadratic equation. And so since it's quadratic, I need to set that thing equal to 0. And so in this problem, I subtract 8 from both sides, and I subtract x from both sides, rather, and then I also subtract 8 from both sides. And so you get 0 equals 9x squared minus 13x minus 4, like that. Not the easiest factoring problem in the world, but it is factorable, believe it or not. You've got 9x here and x here, and a 4 and a 1, like that. Let's see, I don't think now that I look at that that's actually right, because that's going to give you the wrong sign on the 4. Let's see. How is that going to factor? Anybody see how that factors? I'm pretty sure it factors. Actually, I think I probably goofed up here. I don't think that this thing is factorable. It's not factorable. And I'm going to say, oops, because remember I made this problem up, and I think I made an arithmetic mistake at the beginning of the problem, and so it's not factorable, and so at this point we wouldn't be able to solve this equation. So I'm going to say not a quadratic we would see at this point. Later on in a couple weeks, we'll know how to tackle that kind of an equation. And we've done the hard part to this problem, was the squaring both sides and everything. It's just that you end up with an equation that is not factorable at the end. And so, so it would leave us with something that we would have a difficulty solving at this point. And like I said, I made a mistake at the beginning. When I wrote the equation out, I made it up, and I was something I wasn't paying attention to, and made an arithmetic mistake at the beginning. But that's okay. We did the hard part of the problem. So, all right. So your homework to be looking at out of the textbook. So textbook homework. This is in section 9.5. Page 1071. I would definitely want you to try to look at 345 through 371 odd. That's 371 odd. And then probably also 377 and 381. 377 and 381. And then in section 9.6, we haven't quite finished 9.6 up. but we've gotten pretty far in that. This is page 1088. And on that page, I would like you to look at problems 393 through 415 odd. All right, 393 through 415 odd. So, all right, so I'd be working on that over the weekend, definitely. I have office hours on Sunday evening and Monday evening before class. I'll also be around for office hours 11 to 12 today and 1 to 2 today as well. So come by online office hours, definitely. Does anybody have anything that they need to ask about before we shut it down? Anybody have any questions?
No questions for me.
Okay, thank you, Jose.
I'm good.
Charlotte, you're good?
Yeah, I don't have any.
Janessa's good. Justin's good.
No questions.
Sandra is good. And Anne-Marie, I think, is not talking today. So, all right. So if there are no questions from anybody, then have a great day. And, for all of you who are listening here live, those of you who are watching this video later, please come by my online office hours for help. Also, email me if you're looking for your graded exam. Be looking for your exam 1 grade on your WebAssign gradebook. Have a great day.